So now I just want to go over what the general relationship is between a rate of change function and assigned area enclosed by that function. We saw this in the context of velocity and displacement, or speed and total distance traveled, so I just want to generalize this a little bit. So if you look at the bullet points here, suppose you have a rate of change function. The signed area enclosed by the rate of change function is equal to the total amount of change. I've just put up a couple of examples of this just to show you what I mean. Um, Let's suppose, for example, that the function measures gallons of water that drip per unit time. I've used centuries here. Gallons of water that drip per century at time t. Um, so, in other words, what the function is measuring is the rate at which the water is dripping. It's telling you at any given time, let's say at time, let's say that at time the beginning of the ninth century, the water is dripping at a rate of 5 gallons per century. Um, then what you have is a function that tells you at a given time t at what rate the water is dripping in gallons per century. If I find the area under that function on the interval AB, what that's going to give me is the total gallons of water that dripped between time century A and time century B. In other words, if let's say A is 8 and B is 12, that's going to tell me how many, the area, the signed area enclosed by the function will tell me how many gallons of water dripped between the 8th century and the 12th century. And note that the function itself is measured in gallons per century, but when I find the area under it, that quantity is going to be measured in just gallons. That's the idea. If I take a rate of change function and find the area under it, what I get is the total amount of something. Here's another example. I think we saw this earlier in the semester in the other direction, having to do with the rate at which a bear's mass was changing. So if I say that f of t is the rate at which a bear grows at time t, which is measured in kilograms per month. In other words, at any given time t, let's say time t equals 3 months, I'm saying that at this instant in time, the bear's mass is changing at a rate of 50 kilograms per month. Then if I find the area under that function, then the area is going to give me the total amount of mass. If I find the area under that function on the interval AB, that area is going to give me the total amount of mass that the bear added between time t equals a months and time t equals b months. So let's say that I find the interval, define the interval as, let's say, from 3 to 6. What that means is that the area is going to tell me how much mass the bear added between month 3 and month 6. Just to bring this back to the example you saw already, we saw that if we have a velocity function, which is a rate of change, it's a rate at which the displacement is changing in meters per second. When I find, so here I've graphed, on the horizontal I have the time in seconds, and on the vertical I have the velocity, in other words the rate at which the displacement is changing in meters per second. So the area under the velocity function, the signed area, is going to give me the total amount by which the velocity changed on the interval AB. In other words, from time equals A to time equals B, the total amount the velocity, the total, not the velocity, the total amount that the displacement changed between time A and time B is going to be the signed area. So as we can see, we have we're going to be advancing somewhat, increasing our displacement in the positive direction. Then for a little bit of time, we're going to be changing our displacement in the negative direction, which means we're subtracting some displacement. Then we go back to a positive velocity, increasing our displacement in the positive direction. We add all that up and we find out how much the the object changed displacement, how much it added to its displacement between time equals A and time equals B. So if you go back to these examples, it's the same thing. If you add up the area under a rate of change function, what you get is a total amount of change.